Hi, and welcome to our new session here in our chapter on classification. So this is a very basic session simply on the terminology of what linear classifiers are. So we'll discuss their definition and figure out that this is somewhat different than what we mean by a linear model in regression and statistics. We'll talk about linear decision boundaries and what linear separability means for a data set. Okay, so yeah, there's lots of different linear classifiers. We'll discuss a couple of them here in this lecture, and later on then quite a few more. So linear classifiers would, for example, be something like a linear discriminant analysis. Logistic regression would be a linear classifier. Linear support vector machines, I guess it's in the name also, so if you don't kernelize them, they're also linear classifiers. And there's a whole bunch of these. So I guess it makes sense to give a mathematical definition of what we mean by a linear classifier. It turns out that this is not terribly difficult. We have to just watch out for basically one little thing here. So the thing is, so if we have our classifiers, they usually work with something like a score function. So here we'll assume these are not like hard labelers. So we'll assume they either scoring functions or probabilistic classifiers. And I don't really want to distinguish between these two now. So I'll just talk about scoring classifiers, and everything else. Everything works in a similar fashion or in the same fashion for probabilistic classifiers. So if these are multi-class things, multi-class classifiers, there will be a whole bunch of these discriminant functions. And the simple definition for a linear classifier is that this discriminant function can be written as a linear function, and as a linear function in X. So this is a bit different than linear model. In regression, where usually the linear refers to that the model is actually linear and the parameters, here we really mean linear in X. And the idea is that the decision boundary of this linear classifier is going to be a hyperplane. So our definition is going to be that this f of x, or fk of x I should rather say, can be written as a linear function in X precisely, or more precisely than I just said, it's actually an affine linear function. So we should be able to write it like wt transposed or wk transposed times x plus some intercept bk. Okay, there's one little catch, and this is that this doesn't always work for our classifiers. So we'll allow the writing as such an affine linear function possibly after applying some rank-preserving monotone transformation G. So this will be a lot clearer later on if you look at certain examples. So I guess maybe it's a good idea to come with one now. So for example, if you look at logistic regression, which we'll discuss quite a lot in detail later on. So logistic regression you could write as a sigmoid function times theta transposed times x, I don't know, plus some intercept. I guess I'll write it down here. So you can see here there's this linear function on the inside of that, but there's also this transformation of this linear function to a probability. And yeah, we'll just account for that by allowing that. So if you can take your discriminant functions and apply any affine univariate rank preserving function to them, if you take your discriminant functions and you can apply any monotone transformation to them, to arrive at some affine linear function in X, then we would call the classifier linear. So in these W and B's, they are not necessarily our parameters, which are estimated by the model. Yeah, they are just, I don't know, some constants that can be found, so that the structure of this guy here is indeed affine linear. Okay, so can we now show that if that definition holds, that we actually have a hyperplane separating our classes, that our decision boundary is actually a hyperplane? And the answer is yes, and the answer is, and it's actually not very difficult to show this. So let's take a look at it. So let's take a look at a situation where we have actually a tie between two functions, two of our discriminant functions. So this is how our decision boundary was defined, right? And now we said that if we apply our affine linear, if we apply our monotone transformation to this f, we can write it down as a linear function. Now here with a with some wi on the left hand side and some wj on the right hand side. You just rewrite this very slightly, bring it all to one side, and now we can see that this is actually the form of a hyperplane in X, which I've visualized down here. So this would be some hyperplane acting as our decision boundary. It's very easy to show this. So I guess our definition expresses what we want it to express. Here's a further little example. So I came up with a very simple classifier which would be linear, where it's maybe not also totally obvious that it's linear. Well, I guess it is if you've seen this a couple of times, but as a beginner you might have not. So let's say we have some binary classification problem in front of us, and we're just going to model our classes with centroids. So I'll pick some location from the one class here, I pick another location from the other class and pick it there. These are my estimated parameters, and I don't really care here on this slide for this example how we are picking these locations exactly. So one obvious and common usual thing would be to estimate the mean of each class, but you can also just pick some, I don't know, observation from each class which you deem to be a good representation. Can do anything, for the following to hold. So just pick two places. We'll call them, I don't know, mu1 and mu2, and we'll call them, I don't know, the centroids of the classes, the representing locations, so to speak. And our classifier is now going to work in the following very, very simple manner. If we want to classify a new point, we simply compute the Euclidean distance to both of the centroids of these two classes, and we'll pick the class as prediction for which the distance is actually smallest. Okay, so yeah, and for such a classifier we can now also very easily show that this would actually be a linear classifier. So maybe it's a nice idea to talk about this geometrically a little bit. So what I can do is I can take my two classes and their respective centroids, and I can simply connect them with a straight line. So visually I can now easily construct the decision boundary by simply constructing an orthogonal hyperplane and placing that here exactly on the middle of this connecting segment between the two centroids. We can also easily show this algebraically, that this works and gives us the resulting form of a hyperplane. So let's simply calculate our decision boundary. So let's talk about points x, which are equally close to both centroids. So we have our distance d1 and our distance d2. So this is what I marked here in my plot on the slide before. So I have these two distances, and I guess I'm going to be on my hyperplane if the distances are both the same, because then I can't really decide, right? Okay, so we compute the distance to mu1 and the distance to mu2, and the only thing we're going to do now is we're going to, well, actually I'm computing let's be precise, I'm computing the squared distance here, so the squared norm between x and muj. And the reason why I'm squaring this is so I can easily express the norm through scalar products here. Not going to read that out. By now you should really know how to do this. Well, I guess I can read it out for one term. So this thing here, so x minus mu1 and then the squared norm, this is simply x transposed times x, right? So multiply x by x, and these are vectors. So this is going to be x transposed times x minus 2 x transposed mu1 plus mu1 transposed times mu1. And the same happens here for our distance, for our squared distance to mu2. Now we simply stare at the formula a little bit and simplify it just a tad. So the first thing we can notice is that the square term here is the same on both sides. So we just eliminate it. And then the next thing we do to go from here to there is that we bring the linear terms, and with linear terms, the ones including an x on the one hand side, here on the left hand side, and the constant terms, these two guys, I bring on the right hand side. And here you can see this is a linear function in x. This is the form for the hyperplane, and we are done. So easy peasy. Very, very simple proof to show this. So linear classifier is terminology we, I guess, obviously apply to classifiers, to machine learning models, classification models. There's also terminology for data sets, and this is usually called linear separability. So if there exists some hyperplane, some linear classifier, I could say it doesn't really need to be a classifier, just if there exists some hyperplane in my feature space that perfectly separates my classes, like can be two, can be multiple, then we would call that data situation linearly separable. So you can see this here in 1D, where it makes a little bit less sense. You can write that it is applicable, it just isn't really a hyperplane, right? It's just this single point split, so to speak. In 2D, it looks a little bit more intuitive. If you have a situation like that, where all of the blue points go on the left-hand side and all of the orange points go on the right-hand side, and we can squeeze such a hyperplane between both classes without any error, then we would call that situation linear separable. And if that's not possible, I don't know, for example, for this XOR type of data situation here on the right-hand side, well, I guess then we'll call it not linearly separable. Final comments. So sometimes, I don't know, a certain discussion going on whether you can actually use linear classifiers to work with data which is completely non-linear, so to speak. So whether you could use logistic regression, for example, to handle a non-linear situation. And the thing is, so if you allow yourself, or if you allow your logistic regression model, for example, your linear classifier, to act on transformed features, so to produce a, not necessarily separating, but well-performing hyperplane in a derived feature space, in a transformed feature space, then, of course, you can handle non-linear situations in your original input space. So, but this is usually not what we mean when we talk about that, or at least this is not really my terminology. So, of course, if you allow yourself such feature transformations, you can become a lot more flexible. But when I talk about maybe something like a linear discriminant analysis or a linear support vector machine or logistic regression not being able to handle nonlinear situations, what I mean is without allowing ourselves extra feature transformations. Okay. Later on, when we talk about kernelization of support vector machines, we'll figure out an automatic way of performing these feature transformations. Also, I guess you can also say that a neural network learns a certain representation, learns successive transformations of the original feature space to be able at the end be able to apply a linear model at the end, so that prediction still works well. Okay, that brings us to an end here. See you in the next session.